I can get started. All right. First case is a 82-year-old female with no significant past medical history who developed a lump on the back of her head. Her exam, she's neural intact. This is her imaging. Let's see who's on. Silva.
Yep, I'm here.
All right. Tell me what you see.
So it looks like a extraaxial mass kind of at the suprasagittal sinus in the midline. Looks to be kind of heterogeneously enhancing, kind of mixed density, and seems to be, I would say, based in the bone, maybe in the dura.
Mm-hmm. So what are you thinking for this case?
So differential would be hemangiopericytoma, a primary bony, osseous lesion, could be bony or dural metastasis. Yeah, something along those lines.
Okay. So interesting enough, this was actually biopsied at an outside hospital. It was called squamous cell carcinoma. She got radiation and treatment, but it continued to grow. This is also part of the differential here. Osteoma, fibrous dysplasia, meningioma is also part of the differential, and intraosseous meningioma. So we took her to the OR, we resected it. It was involved in the dura, but we were able to scrape it off. And Dr. Saad will talk about the path.
Share my screen. Okay, so this is the tumor. This is what we call pseudopolycytic necrosis. The tumor is very cellular, as you can see here, and there are multiple areas of necrosis. In terms of cytologic features, there is significant atypia and pleomorphism. And what does this mean? It means that there is significant variability in size and shape of the cells. And also there is another atypical feature, which is the presence of these prominent nucleoli. More importantly, the tumor is mitotically very active. In this power field alone, I can see 2 mitotic figures. The total number was 22 per 10 high power field. EMA, epithelial membrane antigen, is diffusely positive. Ki67 is very high, about 40%. H3K27ME3, which recently has been shown to be associated with increased recurrence risk in meningiomas, is lost in a significant number of the tumor cells. And this is anaplastic meningioma in grade 3.
So it was interesting, just mostly because she went to an outside hospital. She had an actual biopsy of this lesion, which came back as squamous cell. I'm not sure where they biopsied, but this ends up being an intraosseous meningioma. This is less than 2% of all meningiomas, and 2/3 of all extradural meningiomas. There's a femoral predilection, and lytic lesions like this one are more likely to be malignant. It's thought to be due to the arachnoid cells being retained within the bone. Obviously, gross total resection of the tumor, and then depending on the grade of the tumor, radiation. So grade 2 and grade 3 meningiomas end up getting radiation to the dura. I just thought interesting case because incorrect biopsy. Next case is a 29-year-old male who initially presented to an outside hospital intoxicated with ultramental status. MRI showed a deep left deep lesion that was biopsied at an outside hospital, and he was shunted as well to treat his hydrocephalus. He was started on treatment, but the tumor ended up growing on treatment. His exam was neuro intact. Let's see who's on. Oops. Victor?
Yep. Series of MRI scans demonstrating a looks like primarily intraventricular mass, homogeneously enhancing. It looks like it's in the third.
You think it's in the third ventricle?
No. Sorry, it's in the primary lateral ventricle.
Mm-hmm. What about this? You sure? Looking at this slice here, I'm not sure it really originates. Maybe more of a thalamic lesion, really, than a ventricular lesion. Is pushing on the ventricle. You can see it's pushing.
Oh
yeah. So what's part of your differential?
So for thalamic lesions, they can, based on this, it could be primary glioma, could be there's a ganglion glioma. Other lesions in this area include metastasis, possibly neurocytoma as well.
What was that?
Neurocytoma as well.
Mm-hmm. I guess others, could be unlikely neurosis or sarcosis, other types of glioma like pilocytic or xanthorachal cytoma. So what would you do for this? How would you approach this tumor?
So this patient was symptomatic, most likely would benefit from surgery then. Given its, if you could go back, I think given its location, you could aim for not only biopsy, but resection as well.
Yeah, so he had a biopsy at the outside hospital, but it continued to grow on the treatment. So that's why he was brought to the OR for further resection of this tumor.
Oh, I see. Yes.
Initially attempted through the Vicor, however, they had to convert to open resection. So Dr. Saad.
Okay, so this is the tumor at low magnification. You can appreciate the tumor is very cellular. Also, we see calcifications. Calcifications are historically associated, not always, of course, with slow growing tumors. Higher magnification, this is what we call pleomorphism. So this is the pleomorphic component of this tumor. So we have cells that are bizarre shaped. Some of them are multinucleated. And this is the xanthomatous component, which are cells with large eosinophilic, slightly foamy cytoplasm. The tumor is a glioma by virtue of positivity for GFAP, and Ki67 is low, is about 2%. So this is PXA grade 2.
So yeah, pleomorphic xanthocytoma accounts for only 1% of primary brain tumors. Typically, these tumors are found in young patients, peak incidence in the second and third decade of life. Just like this patient, there is a predilection for the temporal lobe, unlike in this case, but typically you see these in the temporal lobe. The prognosis is generally good following surgical excision of grade 2. There's about a 90% 5-year survival and 70% 5-year disease-free survival. Local recurrence and malignant transformation is common and happens in about 20% of cases. Treatment, surgical resection, however, and then radiation is not thought to be beneficial except in cases with subtotal resection. Unfortunately, due to the location of this tumor and the thalamus, they were unable to get gross total resection. So the patient's planning on getting further treatment. Next case, this is a 34-year-old female who had a previous resection of a cervical tumor at an outside hospital. She was told she had low-grade cancerous tumor. She had progressive numbness in her hands and worsening dexterity, so she came to see us. This is her initial MRI before her biopsy. Adham?
Yes, so we see multiple series of MRIs here on this sagittal cuts and the axial cuts. You see on the T2, there's an intradural lesion extending from the C2 up to C7 with an I would say it's I'm not sure honestly what's the differential for this tumor.
So first of all, is this contrast enhancing? Is it not contrast enhancing? I don't know if I missed that or not.
Yeah. So
and what's going on at the foramen magnum?
So at the foramen magnum, there's excessive amount of there's a is that
a cyst? Is that a syrinx?
I would think that it's a cyst
Mm-hmm.
more than a syrinx. I would say the syrinx is more towards the, if there's on the T2, the first image, more at the quartz signal change. I'm not really sure what it is.
Okay. So we always talk about the three main categories of spinal tumors. You know what those are?
Intradural,
Mm-hmm.
intramedullary,
Mm-hmm.
extradural, or the
So you said intradural, intramedullary,
Mhm.
extradural, and then there's one more. So intradural, extramedullary.
Got it.
Okay.
Mm-hmm.
All right. So what? So what? Do you think this is? What category of tumors?
I would think that this is more extradural.
You think this is extradural? So here's the dura here, right? So extradural would be out here. So this is definitely intradural. So the question is this inside the spinal cord or is it outside the spinal cord? And based on this imaging, that he's got some contrast enhancement down here in the spinal cord. So this would be under the category of intradural, intramedullary.
Got it.
All right. We'll bump this up a little bit. So Sumed, can you tell me what the differential for intradural and intramedullary tumors are?
Hey, yeah. So the differential for intradural intramedullary tumors, is going to be glioma, astrocytoma. It's going to be ependymoma. In this location, and looking at the scan, it looks like it could very well be an ependymoma causing a syrinx.
Okay, perfect. So, this is the image that we had post biopsy. They did a C1 2 laminectomy here, biopsied the tumor up here. This is kind of a better image, I would honestly say, of the tumor itself. So they actually sent the pathology to UCSF, and the biopsy showed ganglioglioma. Do you agree with that? Do you think that they maybe made a mistake, or is that kind of the diagnosis? Based off of this image here, I would say is probably more telling.
It's hard for me to believe it's a ganglioglioma. I mean, it is very avidly contrast enhancing. It's intradural intramedullary. Like I guess I never would have put ganglioglioma on a differential for me for intradural intramedullary, but I don't know, maybe I should consider it now if that's really the case, but I would be very hard pressed to believe that that's true.
That's fine. That's your opinion. You know, I would tend to agree, considering there's this well circumscribed lesion. But we will now see what Dr. Saad has to say about it.
Yeah, I just was gonna say, great job, but you know, they obviously didn't biopsy the mid cervical lesion because there's no laminectomy above that lesion. They biopsied the cyst wall. And the kind of the sad thing about it is they decompressed the cyst, biopsied the cyst wall, and that's the path that you have to review. But then they sent the patient for radiation, and without addressing the larger tumor. And then that fortunately radiation oncology sent the patient to us to address the mid cervical tumor, and that's the path that you're going to see now. But I was wondering if Dr. Saad could comment on the biopsy results.
Sure. On the biopsy, what I think happens, and this is a very common pitfall in neuropathology, when you biopsy, especially in the spinal cord, when you biopsy an area that is in close proximity to the tumor, the area will show Rosenthal fibers, will show reactive astrocytes, and ganglion-like cells. So this is not an uncommon mistake. You know, every time you guys give us a tissue, we assume it is from the tumor, and I think that's what happened at UCSF. So it is you know, I can understand how a mistake like this could happen.
But if we go back to the post-op MR, if you wouldn't mind, sorry, Michael. If you go back to the post-op MR, you see that the biopsy is very far away from the tumor. The biopsy is at C1, C2, and the tumor is at C5. So they probably biopsied the cyst wall. But what I wanted you to address is the actual pathology form that Michael had in the prior image from UCSF, and they did some kind of I don't know what it is.
You can't read it. It's
Hard to read. Yeah.
Okay. It's some kind of artificial intelligence. I think that they put the specimen through and they came up with the diagnosis of not even ganglioglioma, but astrocytoma. So do you know what that is that they're looking at? I'll tell you what it says exactly. It's a UCSF 500 gene panel final report.
we don't, yeah, basically they do analysis of 500 genes on the tissue, but you have to be certain that the tissue is neoplastic first. That's the issue. Tissue is the issue. We always tell people that.
It says that interpretation is the tumor only sequencing of this astrocytic neoplasm did not identify pathogenic mutation applications. Anyways, I've never seen that before.
Hey, Alan, maybe I can add some historical perspective, because this was there was an epidemic of gangliogliomas within the spinal cord, and you could trace the epidemic to a neuropathologist who had this idea that all of these enlarged ganglion cells were not reactive, but were part of the primary neoplasm. His name was Doug Miller. He wrote extensively about this, and he was the neuropathologist at NYU when Fred Epstein was doing all these spinal cord tumors. So if you look at their pathology characterization of their tumors, a great many of them were gangliogliomas. In retrospect, I think it's mistaken. I think Dr. Saad's absolutely right. These were reactive at the margin of the lesion. And it was a common interpretation. And
Yes.
of course, we put all this faith in this molecular analysis, but Dr. Levy's absolutely right. If you biopsy the peritumoral tissue, this is what you're going to get. This is what you're going to get. If you go back to the original MR, Michael, I think there's some really classic findings on this that are pathognomonic for an ependymoma. If you look at the axial image in the mid one of the three axial slices, the tumor that arises in the center of the spinal cord and is symmetric in the cord is almost pathognomonic for ependymoma. And the fact that it has a polar cyst is also highly suggestive. So I don't know where this person got their care, but I wouldn't send anybody else there.
Okay, so this is the tumor. The tumor is very cellular again, and on higher magnification, you can see what we call ependymal pseudo-rosette. So pseudo-rosette, as opposed to true rosette, the tumor cells are arranged around a blood vessel. And here you can see the lumen of the blood vessel containing red blood cells. True rosette, the tumor cells are arranged around neuropil, cellular processes. And if you look at the tumor cells, they're monotonous. There is no significant atypia or pleomorphism. I do not see mitosis, necrosis, or vascular proliferation. On higher magnification, just to reiterate the monotony of the tumor cells and the absence of atypia and pleomorphism, but more importantly, significant number of the tumor cells have a clear cytoplasm. GFIP is positive, and it has a particular positivity in ependymomas. If you look at the tumor cells, most of them are negative, but the pseudo-rosette is positive, and it is positive in a way that GFIP highlights the processes that are coming out of the outer wall of the pseudo-rosette, because the tumor is trying to recapitulate its origin, which is the ependymal lining. EMA is also characteristic, almost pathognomonic in ependymoma, is that it is positive in a dot-like cytoplasmic fashion, just like in this example. Ki67 is very low. So this is, and this is H3K27M, since this is a practically midline glioma, we always like to rule out diffuse midline glioma, and we ruled it out in this case because H3K27M is negative. So this is ependymoma, WHO grade 2, and the WHO does not recognize a clear cell ependymoma as a distinct entity, but several studies have shown that clear cell ependymomas, grade 4 grade, behave a little bit more aggressively compared to grade 2 ependymomas with no clear cell components.
Perfect, thank you. So yeah, so this ends up being an ependymoma. It's the most common intramedullary tumor of the spine. 60% of all intramedullary tumors, peak incidence within the 4th decade, 39 being the mean age of presentation, associated with NF2. Treatment, gross total resection can lead up to 85% 5-year survival rate, and radiation for subtotal resection or for grade 3 lesions. So next case, let's see, on Turkey. Turkey, you there?
Yeah, I'm here.
Okay, perfect. So 32-year-old female who has a long-standing history of pineal region tumor. She's had 4 resections of her tumor, 3 of them with us. She has undergone multiple rounds of chemotherapy and radiation. On exam, ANO ×3, down gaze restriction, persistent diplopia, but otherwise intact. So this is her scan.
So this looks like, hyperintense on MRI with contrast on both coronal, axial, and sagittal. It seems there's some calcification. I'd say my first differential would be Germanoma.
So, this is a patient who's had multiple surgeries for her tumor. If this is a Germanoma, what is the mainstay of treatment for Germanoma? Do patients with Germanoma typically get surgery?
No, they get radiation.
Right. So you could say that. So there are three main categories of pineal region tumors. So you mentioned Germanoma, which would include yolk sac tumors, and Germanomas. So that is mostly out of the question in this case, at least. What are the two other categories?
You can have pineocytoma or pineoblastoma.
So those are the intrinsic tumors of the pineal region. And what's the third category?
You can also have glioma in that location.
So the third category is kind of like miscellaneous, right? It's glioma, metastasis, you can have melanoma, meningiomas can arise from this area. So those are all part of your differential in a patient like this who has, had multiple surgeries for a pineal region tumor that, continues to grow back. But germ cells tumors being the lowest on the differential. Dr. Saad?
Yes. Okay, so this is the tumor at low magnification. This is what we call basically blue cell tumor. What does this mean? It means that the tumor cells have very scant cytoplasm. You can barely see any cytoplasm in the tumor cells. And the nucleus is hyperchromatic. That's why it appears blue. Given the presence of multiple recurrences and multiple surgeries, it is not a surprise that the tumor is poorly circumscribed. This is the adjacent non-neoplastic brain. And also you can appreciate the presence of brain invasion here into the adjacent brain. In other areas of the tumor, there is a vague papillary formation that is cut in cross section. So this is the lumen of the papillae, and these are the tumor cells arranged around it. So, and also in other areas, there is no necrosis, there is no mitosis, the degree of atypia and pleomorphism is within normal limits. So this is still consistent with papillary tumor of the pineal gland.
Thank you. Oops. So yeah, papillary tumor of the pineal region. This is a new, relatively new tumor entity that was only added to WHO in 2007. It's a rare neuroepithelial neoplasm. It's generally either grade 2 or grade 3. It's a separate entity from pineoblastoma, pineocytoma. Usually it's very well circumscribed and diffusely positive for cytokeratins. Treatment is gross total resection. Just because this is a new entity, there hasn't been much research into what the standard of care is. There's no consensus on chemotherapy or radiation therapy to this tumor. Chemotherapy can include, cisplatin, etoposide, temozolomide, or bevacizumab. This patient has gotten multiple rounds of cisplatin and radiation. Local recurrence is common, and surgical resection is best for overall survival. However, in cases like this where it's multiple operations, each subsequent surgery is more and more risky considering the difficulty of getting to this region. So that's all I have for neuropath.
Michael, maybe you or Dr. Saad can comment on this new tumor. Was this defined based on its histological characteristics, its genetic characteristics, its clinical behavior? Why do we have a new primary neoplasm of the pineal.
Yes, as Dr. Kader said, this was introduced relatively recently in 2007 when I was a fellow. And I witnessed the thinking process about this tumor because it was classified by Dr. Lewis, who's a neuropathologist at Mass General. So what triggered the distinction of this tumor is that, first of all, histologically is different. It shows papillary formation, and it doesn't stain like other pineal tumor, like pineoblastoma or pineocytoma, in that it is focally positive for synaptophysin as opposed to other tumors. And also the behavior. The prognosis of this tumor is relatively good compared to pineoblastoma and other tumors. And so they went back and looked at hundreds of tumors, and they extracted these tumors that are histologically similar. So back then it was pure immunohistochemistry and morphological classification.
And your comment that it predicts behavior, it doesn't behave like a pineoblastoma.
No, the prognosis is much better than pineoblastoma.
But not a pineocytoma.
Not a pineocytoma.
Not a more benign path, not surgically curable.
That's correct.
Thank you.
Any other questions? Okay.
Okay, thank you, everyone.
Good morning, everybody. I can get started whenever we're ready, or if you want to wait a little bit.
Let's start, Dominique. That's great.
Okay.
Thank you.
Sounds good. So good morning. I'm Dominique Higgins. I'm one of the neurosurgery fellows with Dr. Komatar, Dr. Ivan, the Brain Tumor Fellowship. I'm going to talk about some of my research from residency at Columbia, looking at dietary regulation of ferroptosis in neuro-oncologic and neurodegenerative diseases. I have one disclosure is a provisional patent based on some of this research, no financial conflicts. And then just an overview of the talk. We'll start by talking about glioma sensitivity to cell death by ferroptosis. I'll go over what ferroptosis is, this new form of cell death, and how cysteine and methionine deprivation can sensitize gliomas to it. And we'll talk about some of the translational strategies we're implementing to try to treat patients with gliomas with this new therapeutic methodology. And then at the last part of the talk, I'll touch on a different arm of the project looking actually at ferroptosis inhibition for neurodegenerative diseases. So I won't talk too much about glioma because Kater and Victor gave a great grand rounds a few weeks ago on that, and you guys are very well versed in it. But ferroptosis is a relatively new form of cell death under the umbrella of programmed cell death pathways, apoptosis probably being the most popular, but this is an independent arm that was actually discovered by one of our collaborators, Brent Stockwell. And at the core of it, you have cysteine and methionine that essentially serve as the building blocks to help form glutathione, which then interacts with an enzyme to prevent lipid peroxidation, which can result in ferroptosis mediated cell death. And it's iron-dependent lipid peroxidation, which takes advantage of Fenton chemistry, where it uses iron as a mediator to exchange electrons, and you have polyunsaturated fats that interact with free radicals in the cell. And these form peroxyl groups, and if not quenched, they can lead to damage of the lipid membrane, either in the outer membrane or in intracellular organelles. The termination has to be by something that quenches them, and that's where ferroptosis comes into play. It's shown to be important in many developmental and pathological processes. If the cell were to lose the ability to undergo ferroptosis inhibition, it's actually lethal. And it's a critical cellular mechanism for protection against oxidative stress. And like I mentioned, cysteine and methionine at the core of it. And then you can see in this pathway here, methionine feeds into cysteine and forms glutathione, which we'll go into in detail later in the talk. As you can see, just based on the role of metabolism in this pathway, you can see how GBMs are very susceptible to this, just given that they are very metabolic process with high rapid turnover. And also even in low grades, the role of IDH, isocitrate dehydrogenase, is like a key distinguishing pathway in terms of low grades and high grades that is poised to be an important role player in pathogenesis. And as I mentioned, glutathione peroxidase 4 is downstream of all this. Essentially, it's an enzyme that uses glutathione as a substrate to quench the lipid peroxyls that are formed. If left unchecked, they'll go on to form cell death. There are different pharmacologic strategies to target this pathway. The first two are what we'll focus on. You can either inhibit system XC, which is in the top right corner. It's this exchange antiporter that pumps in cysteine into the cell, which is the disulfide version of cysteine, in exchange for glutamate. And so inhibiting that prevents cysteine from coming into the cell. Or you can directly inhibit the enzyme GPX4, which is arguably somewhat more potent. And there's some precedent for methionine restriction in cancer. A few recent articles showed that methionine restriction does sensitize gliomas to chemotherapeutics. And they did one carbon tracing to show that it's very efficacious in terms of its ability to enhance chemotherapeutics. And another collaborator used a different approach, but using cysteine depletion by enzymatic methods, using cystinase in pancreatic cancers, and showed that it dramatically improved survival. Given the blood-brain barrier penetrance issues, though, we thought that it might not be the most viable option for glioblastoma. So we decided to take a different approach by using the dietary deprivation to avoid the blood-brain barrier issues, and we could also increase glioma sensitivity to ferroptosis. And there's two key ways that you can imagine that this works. To have GPX4, the enzyme that inhibits ferroptosis, to work, you need cysteine and methionine. If you just deplete methionine, you have the antiporter that can provide cysteine and bypass that method. to form glutathione. If you just had cysteine depletion, you can have the transsulfuration pathway you can see on the left, where methionine gets converted into cysteine. So that we felt that the two combo hit of methionine and cysteine deprivation, which hadn't been done yet, was the more potent way to go and bypasses some of these potential issues why prior therapies have failed. And on the left, you can see the taurine pathway, which is the salvage pathway after the breakdown of all these molecules, which I'll talk about at the end. And so what we did is we took various glioma lines. The first three, MG1 through 3, were created in a lab with Dr. Knoll and Dr. Bruce at Columbia, which represents more of a low-grade model. We have a few human lines as well. And we did titration curves with RSL3, this GPX4 inhibitor that induces ferroptosis. And we can see that all the lines have varying sensitivity to the drug, but does induce cell death in a fluorometric cell viability assay. The 0185A line was very resistant, and we kind of delved into it, and it actually didn't look like a glioma. It's been kind of a propagated cell line over time. And so we added ferrostatin, which is an inhibitor of ferroptosis, and we saw that in the brown bar, you see rescue of the cells, showing that it's a ferroptosis specific effect. And then in the blue, when we combine cysteine methionine deprivation by removing them from the media in the cell culture, we see that an exquisite sensitivity to RSL3, the ferroptosis-inducing drug, with a rapid induction of cell death and a partial rescue with ferrostatin, which suggests potentially some off-target effects as well, but a large component of it is from ferroptosis. And on the right, we just have a quantification of that data. And then in order to truly say it's ferroptosis, you need to have lipid peroxidation, and there's a molecular readout you can use by fluorometric assay. It's called BODIP-C11, which turns bright green in the presence of lipid peroxidation. On the left, you can see a 2-photon live imaging of glioma cells being treated with RSL3, and then increase in the green color, showing that lipid peroxidation is actively occurring in subsequent cell death. And on the right, the same conditions, but adding the ferroptosis inhibitor, you don't see that uptick in the green, suggesting that the ferroptosis is being inhibited. And this is just a time lapse of that, showing over the 30 minutes, the occurrence of the cell death and the lipid peroxidation. Then we did a flow cytometry for quantification. On the left, you can see low dose RSL3, the ferroptosis inducer, isn't sufficient to induce any ferroptosis. And then when we add cysteine and methionine deprivation, though, this is the low dose RSL3 is now able to induce lipid peroxidation by BODIP-C11, and this is also inhibited by ferrostatin. And you see on the right just a quantification of that, whereas CMD, the cysteine methionine deprivation, is able to essentially have 100 nanomolar of RSL3, the low dose, function like a high dose RSL3, suggesting that it sensitizes the cells to ferroptosis induction. Then we tested other GPX4 inhibitors to see if they have similar efficacy, ML210, and we saw the similar results. And then we did rescue with ZVAD and necrostatin, which inhibit specifically apoptosis and necroptosis to see if there are off-target effects. And those inhibitors were unable to rescue the cells from cell death by RSL3, but ferrostatin, the blue line, was. And typically from prior studies, we know that there are 3 hallmark transcriptional changes you typically see when cells are beginning to undergo ferroptosis: CHAC1, PGS2, and SLC7 layament. And all 3 of them are regulated in the presence of cysteine methionine deprivation, suggesting that the cells are primed to undergo ferroptosis if they were to get a second hit. And we took the cells treated with cysteine methionine deprivation and did proteomic analysis to evaluate whether or not the metabolomic profiles of the cells are different. On the left, in the white oval, you can see the control cells, and the gray oval are the cysteine methionine deprived cells, and you see the clearly distinct profiles by principal component analysis. And then when we look at what are the biggest differentiating pathways that are affected, not surprisingly and thankfully, cysteine methionine metabolism and are among the highest affected. And we then looked at what's happening with the specific components. You can see compared to control cells, there's a decrease in methionine and cysteine, and also some of the salvage pathway components, hypotaurine, which you would expect with downregulation of the pathway. And then we did a fluorometric assay to look at levels of reduced glutathione, which is a building block for the building block of cysteine for a substrate for GPX4 to inhibit ferraptosis. And we see that there's significant downregulation of glutathione in the reduced form in the cysteine methionine deprived cells across about 5 tumor lines. And interestingly, what we did it's called a seahorse analysis, where you look at the electron transport chain components in the cell in real time as you add the different components to look at what's happening with the oxidative phosphorylation. And we also see a dampening of that pathway as well, which suggests maybe a global a suppression of the energetic state of the cell as well. And then we did in vivo studies injecting these tumor cells into mice, and then on day 7, simply putting them on the control diet, or the diet low in methionine and deprived of cysteine. And without any additional treatment, we see a modest but statistically significant improvement in survival with the tumor-bearing mice with just a diet alone. Then we took the brains from those mice that bearing the tumors, and the oval isolates by H&E where the tumor area was. And then we did a spatial mass spectroscopy called DESI-IMS. And when you look at the different lipid species in similar slice sections across the width of the tumor, you see that there's there's definitely an alteration in the lipid species that are formed in the cysteine methionine deprived as compared to the control ones. What role they're playing is something that we're actively investigating, and whether or not this can serve as a signature for efficacy. And so it's a summary of this first part of the talk. We show that RSL3, the ferraptosis inducer, can induce ferraptosis in gliomas. Cysteine methionine deprivation enhances ferraptosis in gliomas and prolongs survival, and results in specific lipidomic and metabolomic changes. So next we want to say, what's our long-term goal here is to try to treat patients with this therapy. So what are our translational strategies that we can use to implement this in glioma patients? And so one obvious one is the dietary strategy. And then the second is to combine that with the drug. There's issues with blood-brain barrier penetrance. So one strategy we're implementing is local delivery of the ferraptosis-inducing drugs in combination with the diet, and then using existing and novel therapeutic agents. And a study we did prior to this, when our collaborator, Simon Cheng from Radiation Oncology, and his postdoc, Ling, showed that radiation actually serves as an inducer of ferraptosis, as a non-canonical ferraptosis-inducing agent, where we treated the cells with a reactive oxygen species detector, DCF, and then gave them either radiation or radiation plus the antiporter inhibitor IKE, and we saw a synergistic response in terms of their uptick in reactive oxygen species in that IKE plus radiation. So one hypothesis, does cysteine methionine deprivation synergize with radiation to actually induce ferraptosis? And so we took those same tumor cell lines, and we either treated them with just the deprivation alone, or with 8-gray single dose radiation to the cells in culture. And in the red bar, you can see that there's definitely a more significant response in the combination treatment strategy compared to either alone. And then when we do the coefficient score to look for synergy across the 3 lines, they're all below the cutoff. And similarly, we use flow cytometry in the presence or absence of the ferraptosis inhibitor, and we see that there's increase in lipid peroxidation by this PODPC11 assay. And then we inject the mice again, and then place them on the diet, but this time added a radiation at day 21. And then we see that the mice that got treated with radiation had the greatest improvement in survival compared to the other groups. And so the IRB that we have submitted and in the process of getting off the ground initially at Columbia and planning for a multi-institutional study, but to have 2 arms where we have patients on the diet for either 3 or 7 days prior to surgery. And then we are working with our physicists to do MR spectroscopy to have a specific readout of some of these metabolites that we've shown that can be altered with the diet prior to surgery. And then in the first arm, have intraoperative sampling of the tumor cells so we can do metabolomic analysis on it compared to the short treatment versus a long treatment and historical controls. And then the second arm is to look at the safety and radiation, pre-radiation patients undergoing either chronic treatment or single dose treatment on the diet or not, and similarly using MR spectroscopy, but only using serum analysis for our metabolomic studies. And it's a multidisciplinary team which took a lot of input from various aspects. We had a great metabolic specialist that works with our pediatric patients that actually is familiar with some of these rare metabolic disorders that and they have to limit cysteine or methionine in their diet. So that was a big input in terms of what we were able to do to try to get this plan off the ground. And working with the Columbia Bionutrition Center, we were able to develop a formula that essentially is a pro-ferroptotic supplement that we can give to patients, and then also a dietary menu that they can eat as well that doesn't inhibit ferroptosis. So we're excited to get that off the ground. We have some industry partnerships that we're lining up as well for funding, and so that's the next phase we're excited about. And then with this last part of the talk, I'll touch on some of the promising therapeutic strategies for ferroptosis inhibition in neurodegenerative diseases. So far, what Ken touched on was enhancing ferroptosis to kill tumor cells. The next thought is that what's happening to the neurons or the normal cells. And then in the cases of neurodegenerative disease, when those cells are sick, can we inhibit this process to protect them? And there's some precedents. The great article in Cell Metabolism looked at 12-15 lipoxygenase and its role in glutathione. And it's actually the downstream mediator of GPX4. By inhibiting GPX4, you activate 12-15 lipoxygenase, which can result in cell death. And then it's also been shown that this lipoxygenase is an emerging therapeutic target for Alzheimer's disease, playing both in a role of tau phosphorylation and A beta plaques being formed. And oxidative stress has kind of long been shown to be a prominent role in tau phosphorylation, as well as just general antioxidant benefits for Alzheimer's patients. So our strategy is to say, can we just locally deliver ferroptosis inhibitors and see if we can aggregate progression of the disease in Alzheimer's models. And our plan is to screen a variety of these models in combination with our Tau Alzheimer's Center at Columbia, and then pilot convection enhanced delivery of ferrostatin inhibitor in these Alzheimer's disease models, plus or minus a diet. And what we're able to do with, we use this TG4510 model, which is based on tau phosphorylation. It has a pretty well-defined progression in terms of the pathogenesis from a cellular level as well as a phenotypic level. So we tried with first implanting these convection enhanced delivery pumps into the mouse brains, and then see if we can detect differences in phospho-tau with or without treatment. Based on the pilot study, it was a little bit variable, but as a proof of concept, we were able to do it. So we're planning to proceed with larger scale studies to see if we can add the inhibitor and inhibit both the tau phosphorylation progression, and we can see changes in ferroptosis markers as well as clinical benefit in the mice. And you can imagine applications to other neurodegenerative diseases as well, in particular Parkinson's disease, which has a large component that suggests that mitochondria is a big player in there. So we're working with another group to collaborate to try to investigate that as well. So for future directions, we're planning to further investigate glioma combinatorial strategies where the radiation or novel pharmacologic agents that are being actively produced. The next step that I'm particularly interested in as I start to plan the next phase of my career in developing my lab, what's the role of the metabolic changes in the glioma microenvironment? We show that the tumor cells are pretty dramatically affected, but what's happening to the surrounding cells, including like the neurons and the immune cells and macrophages and microglia in the environment. What is the diet doing to those cells, and how can we take advantage of this potential differential stress response? And then also, how does this play a role with the different subtypes? We have some evidence that IDH mutants may be more sensitive to this, suggesting that low-grade gliomas could also benefit, but it's something that we're working out. And like I said, continuing to do these studies with linking ferraptosis inhibition in neurodegenerative diseases, which I think is an exciting forefront and a novel area of pursuit for a group of diseases without any reliable treatments for reversing the progression. And that I'd like to thank a lot of people that kind of played a role in this. The Bartoli lab at Columbia, which head by Dr. Canola and Dr. Bruce. Pavan's now one of the interns at Columbia, who is a co-first author with me on our paper that's near completion in revision at Nature Communications. He did a phenomenal job in terms of taking this over the finish line as I went back to my clinical years. And then Angelina Thanasis, a postdocs at Columbia, and Matei, who's a budding neurosurgical oncologist that will be a rock star in the future. Brent Stockwell, who, like I mentioned, discovered this pathway, and his group that helped out with the metabolomic studies, the Chen lab with the radiation studies, and the Siegelen lab with the seahorse oxidative phosphorylation studies, and the Sims lab that's helping us with the sequencing analysis, and a lot of core teams as well that helped out. And thanks to Dr. Ivan, Dr. Komatar for a great first half of the year. Love being here. It's a great team, and I feel privileged to be able to have part of my training here with you guys. So with that, I'll take any questions now.
Hey, Dom, Mike, Ivan, great job. I want to know, is a methionine cysteine restricted diet used anywhere else, or is there any other diets currently out there that kind of mimic that?
Nothing globally. It's been done for in vitro and preclinical studies, methionine restriction, and what's actually been shown is that it actually increases longevity and lifespan. There's a lot of studies in Drosophila and in some more recent studies in mice. And it's unclear the mechanism, but I think it plays into this differential stress response that shows that inhibiting methionine in healthy cells results in neuroprotection and cellular protection, whereas in cancer cells, it has a different response in terms of targeting oncogenes. The closest thing that's similar is just complete calorie restriction or fasting, which also has been shown in cancer cells to be beneficial. The issue is that it's hard to starve a cancer patient because they're already undergoing chemotherapy, quality of life issues, and how long can you maintain that? So the benefit of this is I think it plays into the core, at least one of the core aspects of just complete calorie restriction, but allows the patient to eat without losing the benefit.
Thanks. And was there any synergy with Timidar? Did you guys look at a chemotherapy and if
yeah,
there's
good
any
question.
synergy with that?
Yeah, we did a pilot study looking at Timidar and the diet. The Timidar and the diet itself didn't have any benefit, but when we added with Timidar, the diet plus radiation was slightly better than just the diet and radiation alone, which I didn't show, but that's something that we thought was interesting and supports going forward, just because it'll be part of standard of care. We were just more interested in say whether or not it for some reason hurt us, but we did see a slight increase in benefit with TMZ added into it.
Sorry, and one more question. You
Yeah,
said it a
go
little
ahead.
bit, but in the serum, you're able to measure the levels. So is there a way you can kind of continuously measure it? Like when you do a ketogenic diet, you kind of analyze if you're in ketosis and if you're maintaining ketosis like throughout it. Is there, has that been established kind of assay to kind of follow this in an outpatient setting?
Yeah, so a great question. There are metrics you can use. I mean, you can just measure, your levels of methionine and cysteine, which we partnered with a lab that has testing for that. What we found to be more reliable though is taurine and hypotaurine, just because the body will essentially compensate after a certain amount of time in terms of those specific levels. So it's not an accurate readout of how well systemically you're being affected, but that taurine salvage pathway seems to be the better readout, and so that's what I'm interested in pursuing. The other caveat is that serum changes doesn't really reflect what's happening in the brain, because the brain is a little bit more reserved in terms of its fluctuation in terms of some of these agents, and so you can have earlier serum changes that don't necessarily mean that the tumor environment is going to be affected. And so that's what we're trying to work out is what's the match between those two things. And that's the benefit of the non-invasive measurements with MR spectroscopy, is that maybe that'll give us the signature, but we're also looking at what we can do as a systemic readout to match it. Yeah.
Great, thanks. Great work. Congratulations.
Thanks, man. All right. No more questions, and that's it. Thanks, everyone.